Hello, welcome to another module of this course, Microwave Integrated Circuits. In the previous module, we had saw how basic matching using lumped elements can be done, and how using short lengths of high impedance or low impedance microstrip lines, they can be used to substitute for inductances and capacitances. But I also mentioned that that is not enough because it may not always be possible to have high impedance or low impedance lines of the desired characteristic impedance. It might not be possible to implement them in a circuit, and also the lengths might be too small than that what is feasible. In when we look from a purely transmission line point of view, the matching of circuits is similar to the matching using lumped elements, but a little different principles are involved. Now, signal flow graphs are, as we have already discussed about signal flow graphs in the in previous modules. At that time of discussing, I had mentioned that there are some rules. I had also discussed some way of simplifying a signal flow graph. And in addition to the methods that we had discussed then, there is also something called Mason's rules. So Mason's rules are somewhat of an easier way of achieving the simplification of signal flow graphs. And if we go to the slides on the monitor, then the gain, that is, suppose we have two nodes. If we can come back to the slides on the writing slides. Suppose this is a point, say G, and this is a point H, and say after simplification the gain between G and H is some value K, or say T. So the gain between G and G to H is T. Then, and say there are lots of paths between this node G to H, many complex paths maybe. Then the gain T can be given by a formula, this as shown here. So this T will be equal to sigma K Pk delta K upon delta. Now I'll just give the definition of this Pk, delta K and delta, and we'll take an example to understand what these individual terms mean. Pk is what is known as the path gain of the kth path between the nodes. Delta is a quantity given by this, and delta K is the value of delta using loops not touching the kth path. So it might not be very clear, but let's see an example. Suppose we have a two-port network as shown here with S parameters as shown. Then its corresponding signal flow graph diagram, as we have already seen earlier, is given like this. And so from this signal flow graph, we have to first determine how many paths are there. Suppose we consider the paths between the gain between A1 and B1. Then how many paths are there total between A1 and B1, and how many loops are there in this signal flow graph. So first we note that this is a path, this one. So starting from A1 and going like this is one path. Another path exists between A1 and B1 is like this. We start from A1, go straight and go along gamma L and come back along S12, finally reaching B1. So these are two paths that we have, and a loop is defined as a path which starts and ends at the same point. That is, for example, this path, let's say this path starts from A2, goes all the way to B2, and then comes back to A2. So this is a loop. That's why. Now, So between A1 and B1 there are two paths, hence applying that Mason's rule formula that I just showed earlier, gamma in equal to, that is the gain between B1 and A1, should be given by this formula, that is path 1 gain multiplied by delta 1 plus path 2 gain multiplied by delta 2 upon delta. Now let us go back to the definition of delta. Delta is 1 minus the sum of all individual loop gains. So if we have one loop, then we will have only one loop gain. If we have two loops, then we will have two loop gains. So this term within this bracket refers to the sum of all the loop gains. That is, if there are two loops, then the gain of loop 1 plus the gain of loop 2 plus the gain of loop 3. Now this term under this bracket refers to sum of the loop gain products of all possible combinations of two non-touching loops. Now imagine this is the signal flow graph diagram which we were considering earlier. Now consider a case where there is another loop, and these two loops do not touch each other, so then they become non-touching loops. And then say there is another loop in some signal flow graph diagram which also does not touch the other two. So we have three non-touching loops. Now three non-touching loops, if we want to choose any two of those three, we can do that in three ways. That is loop 1, loop 2 together, loop 1, loop 3 together, and loop 2, loop 3 together. Now this term under this bracket shows the loop gain products of all possible combinations of two non-touching loops. So if we take two loops at one time, that is say loop 1 and loop 2, if we find out their loop gain products, loop 1 and loop 3, loop 1 and loop 2, loop 2 and loop 3, so we will have three product terms, each containing the products of two non-touching loops. So if we have three non-touching loops, we will have three terms within this bracket. And then this term is an extension of this concept, where instead of considering two non-touching loops, we will be considering three non-touching loops, and so on. All these, so as long as we have any such combinations, if we say have 5 non-touching loops, then we will have this term as well. If we do not have 5 non-touching loops, then this delta will end here. If we do not have more than 2 non-touching loops, then our delta term will end here. And delta k is the value of delta using loops not touching the kth path. So if we have any loop touching the kth path, then that loop will not be considered while finding out delta k. All other loops which do not touch the kth path will be considered while finding out delta k. I hope I am clear now. So then coming back to our 2-port circuit as shown here, the path 1 gain is simply S1, the gain of this path S1. If we go from A1 to B1 along this path, it is S11. The path gain of path 2, that is starting from A1 going straight, turning and then returning to B1, is S21 multiplied by gamma L multiplied by S12. And then what is delta? How many loops do we have? We have only one loop. So then delta will simply be 1 minus the loop gain product, which is S22 gamma L, and that is what we have written. Now delta 1, this path does not touch this loop, hence delta 1 will be same as delta, and this path starting from A1 and ending at B1 touches this loop, and therefore the only term within delta that will be left using loops that do not touch the path 2. So, we do not have any loops which do not touch path 2, hence our determinant 2 or delta 2 will simply be 1. So, then now putting all these values in this equation, if we multiply P1 times delta 1 plus P2 times delta 2 and this whole by delta, we get this as the value of gamma n. Now, I think we had also discussed this formula earlier, but then that time we had done it analytically using equations. Using these Mason's rules, we can if we have any given signal flow graph diagram, we can find out the simplified gain between any two nodes without going into those signal flow graph reduction techniques that we had studied earlier. Now, let us see some applications of this. Suppose we want to find out the transmission coefficient, that is T21 given by B2 upon A1. Let us go back to, so here we have to find out B2 upon A1. There is only one path between B2 and A1, which is along this path S21. Hence, P1 is equal to S21. Delta remains the same, and since this path P1, see this starting from A1 to B2, it actually touches this loop, and by when I say non-touching, it means non-touching at all, including nodes or paths. Nothing in this loop should touch any point, nothing in this loop including the nodes and paths should touch anything in this inner path, in this main path, including the nodes or any subpaths. So, then P1 is given by this, delta is given by this, and delta 1, that is the loops which do not touch P1, there are no such loops, therefore delta 1 is equal to this. Hence, this transmission coefficient is simply P1 delta 1, that is S21 multiplied by 1 over delta, which is 1 minus S22 delta. Now, in microwave engineering, we shall of course be studying this in more details. This term power gain or operating power gain comes across frequently. Now, what is this power gain? It is like suppose we have a 2-port network with a load connected, then the total power that is actually delivered to the load. By actually delivered means actually not that it should not include that component which is reflected from this interface, over the power delivered to the network. That is, if we have a source, then some part of the power, incident power from the source will be reflected back, and some power will enter the network, this network. So, power delivered to the network refers to only that component of the input power which actually enters this network and is not reflected. So, that is why Gp is given by PL upon Pin, and then PL is simply, if suppose B2 is the reflected wave at port 2 at the output port, and A2 is the incident wave at port 2 or the output port, then PL will simply be B2 magnitude square minus A2 magnitude square, and Pin will simply be A1 magnitude square minus B1 magnitude square. Now, in terms of if we simplify this, or if we take B2 common from here and A1 common from here, then we can, this equation becomes equal to this equation. If we, in fact, we can do it manually. Let us try to establish this relationship. So, we have Gp equal to B2 magnitude square minus A2 magnitude square upon A1 magnitude square minus B1 magnitude square. If I take B2 common here and A1 common here, then this becomes now what is this A2 upon B2? If we draw our network, this is B2, ready, A1, this is B1. What is this A2 upon B2? A2 upon B2 is nothing but gamma L, and B1 upon A1 is nothing but the input reflection coefficient. Therefore, our equation for GP becomes now we have already just now found out the value of this gamma in, and the transmission coefficient B2 upon A1. So then this simply becomes equal to 1 minus gamma in square S21 square 1 minus gamma L magnitude square upon 1 minus S22 gamma L square. So this is the final value of the GP. So in summary, signal flow graphs are very frequently used, as I had mentioned earlier, because when we have a large number of ports in any device, it becomes very tedious to actually write all the analytical equations relating the incident and reflected waves for all the ports. Instead, it becomes easier if we represent the entire microwave device with its various ports using signal flow graphs. And then signal flow graphs can be analyzed using various methods, some which we had discussed in previous modules, the signal flow graph reduction techniques. In this module, we have studied a very somewhat systematic way of analyzing these signal flow graphs, which is called the Mason's rule. And I also showed you how we can apply this signal flow graph reduction techniques using Mason's rules to find out the transmission and the reflection input reflection coefficient of a two-port network. And then after finding out this transmission coefficient and the input reflection coefficient, we plugged it in the equation for the power gain, and we derived an expression for the power gain. In the next modules or future modules, we will be defining some more power gain terms, and we'll see that for various situations in a transducer, various definitions of power gain can be used, and some are more practical or more useful, but then from a design point of view, other definitions can be useful. And also in this module, we have covered about microstrip matching networks and how to use the Smith chart to obtain the lengths of these microstrip matching networks. Now, especially I want to emphasize for this microstrip matching networks, please go through the example that I had shown, and it is also given in the notes accompanying this module. Please go through it to get a better grasp on it. And to get an even better grasp on it, I believe it would be correct to practice some of these problems, especially those given in the book by Gonzalez, Microwave Transistor Amplifiers by Gonzalez. Please see the examples given in the book and also the problems given at the back side of the book. Thank you.